class, we discussed briefly about the 3D problem and we went through the procedure. We went through the method to calculate the principal stresses, etc. Now what I'm going to do here is evaluate these principal stresses over here, okay, and see what are the values we get. We need to discuss whether we get a positive value of sigma 1 and 2 or negative values of or mixed positive and negative values. Okay, so let's just calculate these values, assuming these are the values here, and let's try to calculate the values here. So the first one, we need to calculate the term in the bracket. So 47.1 over 2 square. So I'm going to just calculate it as tau. Before I do that, let me clear here. Okay. So square root. So this will be the maximum shear stress we are calculating. So 47.1 over 2, the whole square, plus 14.5 square. This is the value we get, 27.65. Let's calculate sigma 1. Sigma 1 is going to be 47.1 over 2 plus tau max gives you this value. The same way, sigma 2 is going to be minus 4.106. Okay, so let's go to the notepad here. Let me note it down here. Sigma 1, the value is 51.2 approximately. And then we get the other value as minus 4.106. I'm going to write it as sigma 3. There is a reason why I write it as sigma 3, minus 4.106. Why do I write it as the sigma 3 value? For that, let me go back to the slide and note down what are the stress components we have calculated. The stress components are sigma xx is equal to 47.1. Let's assume it is in megapascals instead of kpsi. And then tau xz, you get minus 14.5 megapascals. So if we write the stress tensor, we are going to get sigma xx component as 47.1, xy is 0, however xz is minus 14.5. And all the other components are 0. So when you write it in 3D, this is the stress tensor. Even though it is a 2D problem, this is the actual 3D stress tensor. What does this mean? This means that one of the diagonal values is actually it is one of the principal stress values, which means here in this case, in our case here, sigma 2 is actually equal to 0. So in exams, when I ask you what is the absolute maximum shear stress, we need to be careful here. Okay, because here sigma 1 and sigma 3, sigma 1 is positive, sigma 3 is negative. So the absolute maximum shear stress will be sigma 1 minus 3 over 2, which you will find is equal to the tau max value, which we have calculated here. Tau max is 27.656. So if you check, you will, if you check sigma 1 minus 3 over 2, you will find it is equal. Okay, so add these two quantities up. Sigma 1 minus 3 will become 51.2 plus 4.106. So you are going to get some value 55 something, and finally maybe 56 something, and finally you will have the value 27.656. We can in fact check. If I calculate S1, minus S2 divided by 2, I'm going to get 27.656. Okay, so this is the absolute maximum shear stress. But suppose that sigma 1 and the value which I get here is positive instead of negative 4.106. So in that case, sigma 3 will be 0. So when you are apparently solving a 2D problem, it is actually a 3D problem where the other stress components are 0, and one of the stress components with a 0 is actually one of the principal stresses. So we have to take this into account. Never forget to represent your stress tensor as always as a 3D stress tensor. And when you do that, one of the values will come out as the principal stress value. Okay, this is very, very important when you are figuring out what is the maximum shear stress. Okay, so we are done with that problem now. Let's move on. This is another problem we have already solved. I'm not going to solve it. So I'm going to skip this.
Doctor, I have a question.
Yes.
But if he asked for the maximum in-plane shear stress?
The maximum in-plane shear stress would be in the previous problem, it will be on the XZ plane. So if you are asked in-plane shear stress, then it will be here XZ plane, right in this plane, which is the tau max value which you calculate based upon the 2D stress tensor. Is that clear?
Yes, clear, Doctor.
Okay. When I ask absolute maximum shear stress, then it is in 3D. In plane shear stress, it is just in 2D. That's the only difference. Okay, so let's go to this problem. We already solved it for circular cross section, so I'm not going to go through that. This is a very simple case. You can go through the problem by yourself and try to solve it. So let's see other formulas for finding out stress. For example, if you have closed thin wall tubes, what is the shear stress when you apply a torque on it? So the formula is simple here given. You can directly use this formula, torque over 2 AMT. What is AM? AM is the area enclosed by the median line. You see the dashed dotted line in the center, that is the median line. The area enclosed by this median line inside the median line, that area is called as AM. Okay, so all the central area inside the median line, that will be the area AM. Usually it will be circular, and you can figure out what is AM very easily using pi r square formula. What is the thickness T? T is the thickness of the tube. That's it. So just substitute and calculate what is the shear stress. Very simple way to calculate this. Theta 1 is the angle of twist for a length Lm of the tube. This is the formula you have to use. G is the rigidity modulus, T is the thickness, Am you already know. Sorry, Lm is not the length, rather I think it is the perimeter involved here. 1 second. Okay, so Lm is the length of the section of the median line. So take the median line. If it is a circular cross section, it will be 2 pi r, okay, depending upon the radius of the median line. Okay, so let's see a simple example on how to use these formulas. So you have a hollow tube which is of square cross section here, 40 inches long, 3.6 inches wide, 2.5 inches height, and 1/8 of an inch thickness. So you are given here an allowable shear stress. Allowable shear stress and the rigidity modulus or shear modulus G, that is also given. Estimate the allowable torque T. So we have to reverse this formula here. We need to find torque. Substitute tau allowable here. Evaluate these quantities, multiply, you will get what is T allowable. Okay, allowable torque. Very simple formula. Let's go to the formula here. Calculate Am, the area enclosed by the median line. The thickness is 1/8 of an inch. So which means we have to draw a median line right in the center, going through the center of the square here. Okay. The outside dimensions are 3.6 inches. So I'm going to draw two rectangles. Okay. And then let's draw with a different color, right in the median line with a different color here. So let's assume this is the median line. We know the thickness, the dimensions, so we need to get the dimensions of the median line. So 3.6, thickness is 1/8. So half of 1/8 here, half of 1/8 here. So 3.6 minus 1/8 will be the length here. Okay. So this length is going to be 3.6 minus 1/8 inches. And similarly the height here is going to be 2.5 minus 1/8. Why did I subtract 1/8? Because right in the center, you will have half the length on the top, half the thickness on the top we have to subtract here, and half the thickness here. So both of them together becomes 1/8. Okay, so 2.5 minus this, multiply these two lengths and calculate the area inside the blue rectangle. Okay, so this is the area. The perimeter will be nothing but this length plus this length times 2. Okay, so that's what we are doing here and here. So we have the lengths, and tau allowable can be easily evaluated. There is nothing here, not very difficult problem. Estimate the angle of twist. We have all these quantities. Substitute tau allowable, Lm we have, Am, thickness, G, all the values are given. Substitute and calculate in radians. The value calculated the angle of twist will be in radians. If you want to convert that into degrees, then you have to multiply by 180 over pi. That's it. Okay. If you do that, multiply this value by 180 over pi, you will get it in degrees. So what else? Okay, so this problem is done. In the above problem, compare the shear stress of a circular cylindrical tube with an outside diameter of 1 and an inside diameter of 0.9 inches. So if you want to compare what is the shear stress for this particular case, we can substitute for tau max dr times over j, substitute the values, and this is what we get in terms of T. Shear stress will be T over 2 AMT. Apply the same formula and let's see here what they are doing here. Okay. So there are two formulas we need to compare the values with. So one is for the circular tube, the original formula, and then we use this particular formula here to evaluate the shear stresses. And we want to compare the values. So using this particular formula, this is the result we get. So there is some difference in the values, about 5% difference. Okay. In the case of open thin wall tubes, in the previous case it was closed. So the thin wall tubes could be open as well. If it is open, then the formula for torsional stress is evaluated by this formula here. So which is 3T over LC square. What is L? L is the length of the median line. C, on the other hand, is the wall thickness. Okay, so in this case, this is the length. In this case, it will be whatever is the length here, up till a certain arc length. And similarly, for all open tubes, you can evaluate what are the total lengths. Okay, length of the median line. C, wall thickness can be also obtained. Okay. Okay, so some discussion on this particular topic. We have shear stress, which is inversely proportional to C square according to this formula. Angle of twist is proportional to C cube. From here you can see, take C to the denominator and you will see that θ1 is inversely proportional to C cube. For small wall thicknesses, stress and twist become quite large. We can see that as C gets smaller and smaller, especially if C value is less than 1, then you are going to see what happens to the shear stress. It will increase. Okay, the tau value will increase and the twist also will increase. Okay, so again some comparisons are given depending upon the ratio of wall thickness to outside diameter. Let's see here. Compare thin round tube with and without slit. So we can do a comparison for a closed tube and open tube. Okay, so basically take this formula and the formula given here, and we can make a comparison in the shear stress values. So they have asked you to try different combinations here, and you have different ratios of wall thickness to diameter. Again, calculate what are the shear stresses and how it varies, and if you plot it, you will get relationships. Stress with slit is 12.3 times greater. So basically, if it is an open tube, In comparison to the closed tube, the shear stress will be 12 times greater, and the twist of the slit is going to be 60 times greater. So what does this mean? It is better to have a closed tube than an open tube. In some example problems for open tube, you have a 12-inch long strip steel. The dimensions are given. If the allowable shear stress is given, shear modulus is given, find the torque and the allowable shear stress and the angle of twist in degrees. Just apply the formula. We need to just apply the formula, substituting for allowable shear stress. The torque values we get, theta value, this is the value we get. Okay. And what is the torsional spring rate? That is going to be based upon the torque and the theta value, T over theta. So the spring rate of the torsion spring can be written as K times theta. So from this formula, we get KT value equal to the ratio of these two values, and this is the spring rate we get. Okay, so let's see here. Now, there is also a different formula. So this is for an open shear stress for an open cross section here. We also have for rectangular cross section, what is the shear stress formula? And based upon that formula, we are calculating what is the allowable shear stress, and we get 55.72. So again, we can see some difference with respect to the values calculated here, 5.6 degrees, 5.5 degrees. Spring rate also we can calculate, and we get difference in values, 624 and 574. Because the angle of rotation here is less than 1, very small value, there will be huge difference in the values of KT calculated. Okay, so last few concepts to go through in this chapter. You have to recall what is stress concentration factor. We get the stress concentration factor KT for normal stresses and KTS for shear stress from graphs which are called as Peterson's graphs. For various geometries and various types of changes in geometry, for various loads, we have different Peterson's graphs. So for a shaft, it is given here, subjected to bending moment. This is the Peterson's graph to be used. If we apply a torque, a different Peterson's graph will be used. So depending upon what kind of load we have, what kind of geometry we have for the object, and what kind of geometrical changes we have in the objects, depending upon it, different Peterson's graphs will be provided, and you will have to extract the KT or KTS values from the Peterson's graph, and then evaluate what is the maximum normal stress or maximum shear stress. When you have a hole in a plate, for example, away from the hole, the stresses are uniform, but when you get near the hole, there is increase in stress, be it normal stress or shear stress, and this is called as stress concentration phenomena. And the way to calculate maximum stress analytically, not analytically, rather by empirical formula, is by using the definition of stress concentration factor. So in the case of a plate, for example, if you are given what is the diameter here and the width of the plate, based upon D and W values, you will find what is the ratio in your particular application, and then from the Peterson's graph, you can figure out what is the KT value. In this case, around, let's say, 2.3 approximately. And then he will use it here. Now, this stress concentration factor is for static loads, not for dynamic loads. We have different stress concentration factor in the case of dynamic loads. We will see fatigue stress concentration factors on chapter 7 on fatigue stresses. So this is particularly for static loads. The second question is, how do we use this factor for ductile materials and brittle materials? The rule is always use the stress concentration factor in case of brittle materials. Always use. Okay, use KT or KTS. However, if we go for ductile materials, the question to be asked is, can we allow local plastic deformation? If you can allow in your design local plastic deformation, then we can neglect the stress concentration factors. However, if in your design you cannot allow local plastic deformation, as it may lead to loss of function in your particular application, then you have to use the stress concentration factor even in the case of ductile materials. Okay, did you guys understand this? Did you understand what I said?
Yes.
So again, in the case of ductile materials, if you can allow yield local plastic yielding, then you don't need to use. If you cannot allow local plastic yielding because of loss of function, then use it. In the case of brittle materials, always use it because brittle materials fail catastrophically without any warning, without any plastic deformation. Therefore, for brittle materials, we need to use it all the time. Okay, so let's see here. So the same discussion what I said is given here with static loads, ductile materials, the highest stress fibers yield first. So in the previous case where we have the hole here, the highest stress appear near the hole, and these fibers are subject to plastic yielding first, and then it starts to spread out. As you increase the load, the plastic yielding slowly goes out to the other fibers. Load is shared with the next fibers, cold working is localized, the same thing, yielding is localized. Overall part does not see damage unless the ultimate strength is exceeded. Stress concentration effect is commonly ignored for static loads on ductile materials because you can allow local yielding. Okay, so what are the ways we can reduce the stress concentration effects? So again, since we have the stress concentration effects coming into picture because of change in geometry, geometry is the key. Geometrical design is the key to reducing the stress concentration effect. So when you have, for example, a stepped shaft like this, most of the shafts will have a shoulders because we want to mount the shaft on a bearing, and bearing has to be located in a particular place, and usually they are located with these types of shoulders on the shaft. Because of these shoulders, there is a change in geometry. Change in geometry leads to stress concentration effects. However, we can reduce it by playing with the geometry again. How do we play with the geometry? Provide an undercut on the shoulder. That reduces the stress concentration effect. There is also the providing a shoulder relief groove here on the larger diameter, a large relief groove, then it reduces the stress concentration effect. Again, provide a small width relief groove with a small width, but maybe it is a little bit deeper, and in this case also it reduces the stress concentration effect. So how did they obtain these geometries? By finite element topology optimization. So using in your answers, for example, if you use topology optimization, you can reduce the stress concentration effect. So I could give you a simple assignment group assignment for you. Maybe somewhat later in ANSYS, you go and model, for example, a stepped shaft like this, and you want to reduce the stress concentration effect. That is, you want to minimize the stresses developed in this area, especially when you apply a torque on the shaft and bending moment on the shaft, then that should minimize whatever is the stress that occurs in these locations. You can use topology optimization and try to obtain a change in geometry such that it reduces the stress concentration effects. Okay, so maybe once you finish the midterm, during your holidays, you can work on this as a group, work on this small assignment. Okay, so very simple geometry you produce, try to do topology optimization. If you go to YouTube, you will find many videos that explain to you how to do topology optimization. Go through those videos, try to apply it, and submit your results. Okay, so let's go. I will not go through this example. This is very simple case. You can go through the example, read through it, and see how they figure out what is the stress concentration effect KT on the maximum stress. Okay, all right. You can also try in your ANSYS problems like these, where you just create a plate with a hole of a certain thickness and apply load. Fix one end and apply load at the other end and see how the stress varies near the hole. You can check it. Okay, more formulas here. This is the case where you have a pipe that is subjected to a pressure outside and a pressure inside. For example, in offshore structures, if you have a pipe coming out of or going inside the seawater, okay, it will be under huge pressure. Maybe you are pumping out oil from under the ground inside the seawater, and then this will be the case. So if PO is the outer pressure, PI is the inner pressure, and you have a pipe designed in this manner, you will have what kind of stresses might develop. In this particular case, we are not going to write the stresses in Cartesian coordinate system as sigma xx, y, etc. Rather, we are going to write in the cylindrical coordinate system. And in the cylindrical coordinate system, you have sigma RR and sigma TT, tangential stresses. So what are these stress components you will see in cylindrical coordinate system? You write it in a cylindrical coordinate system, you are going to see these are the components. The normal stresses, as usual, it will be in the diagonal. Then shear stresses becomes R, T, tau, R, Z, etc. The shear stresses will still be symmetric. But these will be the components. So in this particular case, we have only sigma RR value and sigma TT value. All the rest of the components are 0 because of the pressure here. There are no shear components. And we calculate these components by using this formula where Ri and Ro are the inner radius and the outer radius. Okay, just use this formula and evaluate what are the stresses. So since all the other components are 0, this also means sigma TT and sigma RR, they are the principal stresses as well. Okay, principal stresses as well. Now if the outside pressure is 0, the formulas simplify again. And we can see how the stresses vary. Normal stresses, the sigma TT component, this is in the theta direction, and the stress in the RR direction. Okay. If the ends are closed, then the longitudinal stress, this is the sigma ZZ component. Usually the pipes are running several meters long, so we can regard them as the ends of the pipe not being closed. But if it is a short pipe, maybe we can consider them as ends being closed. If the ends are closed, then this is the sigma ZZ quantity. And we can also think of a pressure vessel in this case, thick walled pressure vessel. We also have formulas for thin walled pressure vessels. These formulas you have seen in your solid mechanics or the mechanics of materials course. It is actually the same formula here. So this is for cylindrical pressure vessel, thin walled pressure vessels. And we have again sigma TT value, T max, and we have sigma ZZ. Let's see here. So these are the formulas for longitudinal stress. You can go through the example, simple substitution here. So I'm not going to solve those problems. There are also formulas to calculate stresses in the case of objects like flywheels. You have rotating flywheels, then we need to find what is based upon the cylindrical coordinate system again, what is the based upon the speed of rotation of the flywheel, what is the radial stress, normal stress, and the tangential normal stresses. They are again found out by using the formula here. Rho is the density of the material, omega is the speed of rotation of the flywheel or any rotating disc in radians per second. Nu here is the Poisson's ratio. Ri is again the inner radius, Rho is the outer radius. So just use the formula, substitute, and we can calculate what are the stresses developed in rotating discs. Now we have seen a bearing, on a bearing, a shaft is mounted. Okay, most of the times the shaft has a slightly larger diameter than the inner bore diameter of the bearing. So how do you fit the shaft into the bearing? We have to use some kind of a hydraulic press and force fit that. So these are press and shrink fits. These are such fits are called press and shrink fits. And because there is force acting between the inner rays of the bearing and the shaft, outer surface of the shaft, there will be stress developed on the shaft, outer surface of the shaft. So we need a formula to evaluate what is the stress developed on the shaft surface. So how do we do that? The pressure which is applied onto the shaft surfaces or the inner surface of your bearing is calculated by this formula. If delta is the difference between the radius of the radius of the shaft and the inner radius of the bearing, for example, then based upon the delta value we can evaluate here. So here you can see R refers to the radius of the shaft here. Then we have R naught, which will be the outer radius of your bearings. Ri is the innermost radius of the hollow shaft. So if your shaft is hollow, then Ri value will be that value. If it is a solid shaft, Ri will be 0. Okay, so based upon that, this is the formula to be used. EO is the Young's modulus of the material of the bearing, which is usually outside. O stands for outside. EI is the Young's modulus of the material of the shaft. And similarly, we have Poisson's ratio O for the outer material and Poisson's ratio I for the inner material. Based upon this geometric and material parameters, we can calculate what is the pressure. But if both of them are both the shaft and the bearing are made out of the same material, mostly it is not the case. If it is, then this is the simplified formula where EO and EI value become equal. Now, based upon the pressure value, okay, so let's see here. Okay, so now in order to find what is the stress developed on the shaft, we are going to use the formulas for sigma T and sigma R value, which we used for finding thick walled pressure vessels. Okay, so the same formula we are going to use, but what we are going to do is we are going to apply P. Outer is P and the inner value is 0. The pressure P is here, okay, already found. So apply this in these formulas and we get the tangential pressure for the inner member, and in the case of outer member we apply the pressures in the opposite way and we get this formula, okay, for the inner and the outer. Okay, so these are the normal stresses in the tangential direction. We can apply the same formula for radial stresses. Let's see here, if we apply Pi is equal to 0 here, this component will go off. Here this component will go off, and then we can simplify the other components by substituting P not equal to P. Okay. All right. There is also the formula for thermal effects. Whenever temperature increases, all the materials expand according to the formula given here in XYZ direction. Assuming the material is isotropic, alpha is same in all the three directions, alpha delta T gives you the strain in the three different directions. To get the stress, suppose if I restrict this expansion, free expansion of the material, what will happen? The strain will be 0. However, we can get the stress, equivalent stress, by using Hooke's law, E times strain. That gives us what is the compressive stress developed in the material. Now, this is in the case of 1D problem. If it is a 2D problem, then Poisson's ratio also comes into effect, and this is the formula we have to use in the case of 2D problems. In the case of 3D problems, we need a 3D Hooke's law with the temperature effects. The formula is not given here, so we will not solve such problems. Okay, so finally, these are some of the values of coefficient of thermal expansion. Usually for steel, we can see what is the value, typical value in terms of per degree centigrade and per degree Fahrenheit. The values are intermediate. Usually for materials like copper, should be higher. Let's see here, we have brass, magnesium, so copper is not listed over here. Specifically, you can see tungsten has the lowest value of coefficient of thermal expansion. And tungsten is a material classified as a refractory material. Refractory metals. And usually refractory metals can withstand very high temperature. So you will find tungsten is widely used in high temperature applications. We can have tungsten coating onto a particular metal if you want to have high resistance to wear, tear, etc. in high temperature. So tungsten coating can be given. Tungsten is also used in nuclear power plants inside where nuclear reaction takes place. A coating of this material on top of steel can be used. Okay. And even in modern research, it is used, for example, in experimental fusion reactors also, they try to use these tungsten as the material. Okay. Okay. So, are you guys aware of what is a fission reactor and fusion reactor? If you are not aware, fission is what you have in nuclear reactors, nuclear power plants. So there you will find lot of use for tungsten, very high temperature applications. Okay. So again, a lot of research is going on this particular material. For curved beams, until now what we have seen for straight beams is the formula for stresses. For curved beams, we did not see any formula. You cannot apply the formula what we have seen before for curved beams. In the case of curved beams, the formula to be used for stress, normal stress, especially when you apply a bending moment, is given by this formula m times y over a e Rn minus y. So what is this formula? Okay. In the case of curved beams, the neutral axis of the curved beam does not coincide with the centroidal axis of the cross section. Suppose if you take the curved beam like a hook you use in the crane. Okay, so that is like a curved beam. I don't know why it is taking so much time. Okay. So this is an example of a crane hook. You can see in this picture. So this is like a curved beam. The same example is provided here. The cross section, if you see, might be like an elliptical cross section. It's not exactly circular, but elliptical in cross section. And the centroid of the elliptical cross section is here, while the neutral axis is located at a different distance. So Rn represents the distance from the neutral axis to the some point of origin, especially the curvature. Based upon the curvature of the hook, we can find what is the center of curvature. From the center of curvature, we measure all the distances for the curved beam. So the distance from the center of curvature to the neutral axis is given by Rn. To the centroid, it is given by Rc, and any distance measured from the centroid to any material inside the hook, that is measured with R. The distance between the neutral axis and to the point where we are interested in calculating the stresses, that distance is called as y. Y is equal to nothing but Rn minus R. Okay, now how do I find Rn? We know how to find the centroid. Centroid we can figure out as usual. Rn, how do we figure it out? Rn is obtained by this formula, area of cross section divided by integral dA over R. So once we find Rn, then we can find the other quantities. What is E? V is the distance from the centroidal axis to the neutral axis. So this distance is the E, eccentricity. Okay, so we can calculate E and then evaluate what is the stress. Stress at the inner surface, outer surface. Okay, so what is the inner and outer? This is the inner, Ri, and the outer surface will be Ro here. So at this particular radius, we have the stress values again given here. So just use the formula. So the only example problem is again given. You can go through that. All the distances can be evaluated by using the formula, by using the integration formula, and evaluate the distances. So again, I'm not going to go through the method by which the stress is calculated. The only thing you need to be aware of is because of this force here, if you make a cut right in this region, you will also have an axial stress because of the force. This force you have to replace by a force and a moment acting at that point when you make the cut, and therefore you have the stress due to the axial load and the stress from the curved geometry of the beam, curved beam. So we have to add these two quantities up and get the total stress. So this is the stress distribution. For various geometries, again, you are cross-sectional geometries, again, you are given what is the Rn and Rc values, etc. You can go through that. Centroidal axis. Rc is the centroidal axis. Again, a formula for eccentricity is directly given. Finally, we have the formula for contact stresses. What is contact stresses? When two different objects, they roll with respect to each other or slide with respect to each other, then we have the contact stresses, and such problems are called as contact stress problems. They are also called Hertzian stress. Examples: when you have a wheel, metal wheel rolling against on a rail in your trains on a railroad, then this is a contact problem. When two gears or gear teeth touch each other, move with or roll with respect to each other, again you have a contact problem. Rolling bearings. Inside the bearings, you have balls or rollers rolling between two different races. So let's see here. Let me show you the picture and then you will understand what is the case here. So clearly you can see in this picture, you have different roller elements. There is an inner race and an outer race. These roller elements, they are in contact with the outer race and inner race, and they rotate. These rollers, they rotate whenever the inner race or the outer race rotates. And this becomes a contact problem. So design of bearings, actual design of bearings involves complicated calculations for contact stresses, usually through finite element analysis. So let's go back. Again, it is a contact stress problem. So usually contact stress problems are solved using finite element analysis packages, but in very simple cases, we can calculate analytically what is the contact stress. So let us take the simple example of two solid spheres in contact with each other. Okay, so let's start with spheres. And let us say one of the spheres here. So you have a small sphere maybe, and then a big sphere. They are in contact with each other and you apply a force F. In this case, we can calculate when we have the spheres in contact, one of the spheres will indent or cause a small geometric deformation here. And let us assume the circular area of contact between the two spheres has a radius A. So this circular area in contact causing this depression, the radius of that depression is given by this formula. Nu1, Nu2 are the Poisson's ratio of the material of the two spheres, E1 and E2, again Young's modulus of the two spheres. D1 and D2 are the diameters of the two spheres. F is the force you apply, and you can calculate A. Our aim is to evaluate what is the stress in this case. To calculate the stress, first we evaluate what is the maximum pressure right at the contact surface. This is the maximum pressure based upon the EA value. Okay, and then the principal stresses are calculated for spherical contact by using these formulas. So we have sigma 1 and sigma 2, which are equivalent to xx and yy components given by this formula here based upon the P max value, and the sigma 3 value is also given. A we already know. What is Z? Z is the axis here. So let's take the vertical axis as the Z axis, X and Y axis are right on this plane here on the plane of contact. So as we go away from the point of contact down, the distance Z increases. Okay, based upon the distance Z we have here. Notice that Z is with absolute sign. So that means the stress on the sphere on the top and the bottom at equal distance from the top or bottom has equal stress. Okay. All right. So these are the principal stresses, and the maximum shear stress is obtained by this formula for two spheres in contact. So how does the contact stress vary? You are given here as the distance from the center, from the point of contact in the direction of z. Based upon the distance, you have the variation of the stresses. You can see sigma 1 and 2 here, sigma 3 here, principal stresses, and the maximum shear stress. Very high at the point of contact and then reduces and goes to very low value exponentially. We can also have two cylinders in contact. Only in the case of two spheres and two cylinders, we have the Hertzian stresses. Again, we can see B. B is the area of contact here, not area of contact, the radius of the area of the contact. Again, we have similar formula P max here, and then the principal stresses. Again, we can see exponential reduction in the stress values as we go in the distance z. So we are done with this chapter. Let's take a 10-minute break, and at around 9:10 we will come back. Okay, let's meet back again at 9:10. Do you guys have any questions? If you don't have any question, we'll meet at 9:10. See you guys. Can you guys see my screen now?
Yes.
Okay. We'll continue now. Before I continue, I don't know why the attendance is so low. Please inform other students to attend. Otherwise, I will drop them out of this course. Please inform them. If I find too many absences, I will check the previous classes. If I find too many absences, I will forward the names to the department and they will be dropped out of the course. Okay, so before I continue, I posted something on Teams. I wanted you guys to go online and register for the groups. Please, if you have not registered for the groups, please register now. Where do you register for the groups? Again, here you have the link directly here. You can click on it and then start filling up the groups. So let's see if the Excel file opens. Can I get an error? If it doesn't open directly, you can go to files, go over to design project, to the folder design project. Looks like we have some internet issues. It's not opening now. Let's try again. Going to click on design projects. Okay, let's see here. Seems to be some issue. Okay, so maybe since I'm online, I think I'm not able to access this. So there seems to be some issue with the connectivity. Okay, so now it is opening. Click on groups. You will have the Excel file open. Here I see only 2 or 3 groups registered in this particular class. So I can see here one group being registered, 2 groups. I see only 2 groups which are registered. I have already posted a assignment. The assignments need to be submitted by the group. One person in the group will submit the assignment in the Blackboard. Okay, the groups can be formed 3 to 4 students per group, maximum of 4 students, and you need to come online here and register for the groups. If you don't register for the groups, you will not be able to finish your assignments, your projects, and most probably you are going to get a 0 for these cases. Again, I'm seriously telling all the students, register for the group, start working on the project and the assignment. The later you do it, you will have problems. Okay, whatever the reason, if you do not do your work, you will not get any marks for that, and you will not pass the course. I'm telling you right now, if you do not start working, you will have problems. Also prepare for the midterms. If you do not submit the assignments and you do not prepare for the midterm again, you will have issues with the midterm scores. Do not expect me to pass you without anything. Okay, so let's continue with the course now. Okay, so let's go back to a new chapter now. We have finished 3 chapters. All the 3 chapters are review of what you have learned before in previous courses. Now we'll go for a new chapter. And the new chapter is going to be on failure theory. More correctly, it is static failure theory. So what is static failure theory? So first we need to define clearly what is statics and what is a failure theory. Okay, so let's go to the definition of the word statics. Can one of you tell me what is statics? What is statics? Anybody?
Something that doesn't interface with motion.
So lack of motion. Okay, so no motion. Okay. So no motion of what? Of the
System.
components we are considering, right? No motion of components. So this is a static problem, essentially a static problem. We can think of it as a static problem. But let us think of a problem where you have no motion of the beam. Let us say simple problem, but the force F is a function of time, something like, let's say 10 sine omega t. Is this a static problem? Is this a
No.
no? Why it is not a static problem? What happens
Because
here?
there is a motion with respect to the time.
Yeah, so we can say because of the force varying with respect to time, that means the deformation of the object, there is a deformation of the object with respect to time. Okay, maybe we are not able to see with our with our eyes that the beam is not moving. For example, in the bridges, we have dynamic load. All the time, different cars, different types of vehicles they are moving around the bridge. Although the entire bridge is static, still the problem is a dynamic problem. So this is a dynamic problem. So what is a static problem we are going to consider? A static problem we are going to consider is a problem where the stresses do not vary. Static problem. So this is a much more clear definition. Static problem means stresses do not vary. Not that the forces do not vary, and not that the component is static, but the stresses itself do not vary. For example, I can take another case of a dynamic problem. Okay, where you have a shaft, okay, and the shaft is rotating, but the load is same. The self weight of the shaft, it is always acting downward, right? So distributed load of the self weight of the shaft although the shaft is rotating, the load is static. Load itself is static. It is always facing down. Maybe rho g. So this, maybe by looking at the force, you may decide that the problem is static. No, because the member is rotating. In both these cases, if you actually calculate the stresses become function of time in both these cases. Stress is a function of time. Here, stress at any given point is also a function of time. It varies with respect to time. So both these problems are dynamic problems. So a better definition will be stresses do not vary with respect to time. So this is a clear definition of a static problem. Only this chapter deals only with failure theory for static problem. Theory for static problems. Do not try to apply these for any kind of dynamic problem where stresses become a function of time. It will not work unless you have suitable assumptions. Okay. Now in the static failure theory, we are going to see broadly. I'm going to just provide a conceptual map. This conceptual map, we are going to see how we are dividing it into different topics. The first topic is going to be on ductile materials. Failure theory on ductile materials. We are going to see a couple of them, failure theories, and then we will see failure theory for brittle materials. We will also see a special theory for brittle materials, which is called as linear elastic fracture mechanics, which assumes there is a crack present in the material, and we will see how the presence of the crack reduces the life of the material greatly. Especially, we are going to consider what kind of a cracks? Macro cracks. What is a macro crack? It has significant dimensions in the order of millimeters, millimeter order, not micrometers, but in the millimeter order. Then a presence of such cracks deals to what? What kind of effects does it have on the life of the material? That is what we are going to see. Okay, so now within the ductile material, there are a couple of theories. We are specifically going to see maximum shear stress theory, which will be called as MSS. We will also see what is called as distortion energy theory, specifically of the form considering von Mises stress. So here we will see the definition of von Mises stress. When you plot any stresses in your ANSYS software, you will see von Mises stress there, and this is what it refers to. Okay, we will see the definition later. Now, some of the ductile materials which are nearly brittle. Okay, so how do we differentiate between a ductile and brittle material? Based upon the fracture strain at fracture. Based upon this value, the value can be, there is a cutoff value, if I remember 0.05 or some other value. Based upon the cutoff value of the fracture strain, we will classify if it is greater than, let's say, 0.05 or 0.005, whatever the value. Based upon that value, we will classify if it is greater than that value, then it is ductile material, brittle material. Otherwise, it is brittle material if it is lesser. Now, when the ductile material has a fracture strain very close to that of the brittle material, then it will start to behave like a brittle material, in which case the compressive properties, for example, SU, ultimate tensile strength in compression is not equal to in tension. Usually the compressive and the tensile strengths are equal for ductile materials, but in some cases it is not. In such cases, we are going to see Moore's theory. How to apply Moore's theory. In the case of brittle materials, you have Moore's theory again. Then you also have modified Moore's theory. If you take the most recent version of your book, you may have some extra theories given there for ductile materials, extra failure theories given for the ductile materials. You can go through that as well, but I will not go through those particular theories. Linear elastic fracture mechanics, there are equations. You will come across a property called the toughness, okay, fracture toughness value, KIC, critical fracture toughness value. So this is the property we will be interested in. Okay, so this is the whole overall outline of this particular chapter. So let's go to the chapter right off. Okay. So first we will go through why do we need failure theories. For example, in 1D problems, we can just check our stress value. If it is less than the allowable stress value, then there is no failure. Mostly 1D problems are dealt with like this. But what about 2D and 3D problems? We have more stress components. We cannot just compare each and every stress component. Besides, in a 1D, even in a 1D problem, if I rotate the axis or rotate the plane on which I am calculating the stress, there is a maximum direction, principal stress direction, and the maximum shear stress direction. So which particular stress component to compare and which direction I need to compare. So when we start to think about these questions, then we understand we need a failure theory. So we will go through different kinds of failure theory. I already discussed what are the outline of the topics. So let's go to the next slide. So this is an example of a fracture on a drive shaft. And you can see here, this is basically not due to static failure, but due to dynamic loads and dynamic stresses within the material combined with corrosion effects leading to corrosion fatigue. In reality, most of the components you are going to see, they undergo dynamic failure due to dynamic loads. Not only dynamic loads, maybe it is combined with corrosion, temperature effects, and some other effects, and then leads to failure of the material. In this case, corrosion has led to change in properties of the material. The material probably became brittle due to corrosion effects, and then you had fatigue failure. This is a failure due to impact of a lawnmower. So this is the hub. The hub is connected to the shaft of the motor, and at this end you connect a fan blade which cuts the grass. Sharp edges here, it will go and cut the grass. What happened when somebody took the lawnmower around, a pipe was protruding from the ground, it hit the blades, and then you have the hub broken due to impact load again. So this is an example of a failure where you cannot apply the static failure theory here. This is due to impact loads. Impact here cannot use static failure theory. This is dynamic, to be more correct, fatigue load. Again, we cannot apply static failure theory. This is another case of fatigue failure. In a weightlifting machine, you have this bolt which supports weight, and when a man lifts or drops a weight, depending upon the load, again you have increase and then zero load, increase and zero load. You have fatigue phenomena, and then the bolt broke. This is a chain test fixture. Again, this could be due to the dynamic load, but specifically you have change in geometry where you have a hole. Because of the presence of the hole, we have high stress concentration effects and then fracture. And you can see here also crack propagation in other areas because of very high stress concentration factors. This is a valve spring used in IC engines, for example. You might have seen these valve springs. Okay. So let's see a picture. So this gives you a very good idea. The valve spring is used to close and open the valves in the inlet and exhaust of an IC engine. Therefore, it is subjected to loads, compressive loads and zero load, compressive and zero, compressive and zero. So it is a fatigue load in our case as well. And because of that, we have failure again. Now the spring materials are made out of metals and alloys which are plastic, and because of that you have a 45-degree failure. There is shear stress applied onto the springs. We will see the spring chapter how shear stress acts on these springs, and then because of that shear stress we have a failure. Okay. Now, what are the material properties? Before we go to the failure theory, we should understand how we can use the material properties extracted from quasi-static tensile tests, torsion tests, bending tests, etc. Again, quasi-static. What is quasi-static? Very slow increase in application of loads. So the properties here, they are applied for static failure theory. So what are some of the examples of the properties you extract from tensile stress? We are going to use the symbol S for all material properties rather than using sigma. So for example, S ultimate strength, S fracture strength, S yield strength. So these are some of our examples. In shear, we will write it as SSU, means shear ultimate strength. Then we have SSY, shear yield strength in case of ductile materials. Then we have SF, shear failure, fracture strength. Okay, so like this we can have different properties. So usually these properties, they are necessary to design, and we get these properties from published values. Okay, experimental test data is better, but generally only warranted for large quantities or when failure is very costly. Okay, so usually how do we obtain these values? From experiments. It is very clear, and these experimental data, usually they are conducted for a lot of specimens, and you will have a range of data. Okay, so if you plot normal stress versus strain for different steel specimen, you will have a range of data, not just a single value. You will have a range of values which are plotted, and usually from this range of values you will take the 90 percentile data. What is this 90 percentile data? Among all the datas, we will pick the data which is from the bottom at a 90% here. That means below the red curve, only 10% of the items, 10% of the specimen data are available, 90% of the data are above, usually above it. Okay, so this is the data we will pick for the experimental tests to ensure that most of the materials which are manufactured, they come under this particular failure data or the strength properties. Okay, so we will use this 90 percentile data to apply it to most of our cases where failure can result in very harmful effects right from cost to life. Okay. So these are some of the properties we will be using. We will also be interested, especially in design, to use the stress concentration factors, static stress concentration factors. And what are these? They are obtained from your Peterson's graph, just as we discussed in the last chapter. Okay, so I'm not going to go through this again. Okay, so I'm going to skip this also, we discussed it. Okay, so let's start with simple 1D problem. In the case of 1D problem, how would we go about a failure theory? The failure theory is very simple. We figure out what is the strength of the material and we check what is the stress of the material. The stress of the material should be less than the strength of the material. And if that is the case, no failure. So we are going to define what is called as the factor of safety, N. N is the factor of safety, which is defined as the strength over the stress. If this value is greater than 1, we are safe. If not, failure. Okay, so this is a very simple 1D case, but let's go to a 2D or the 3D case. In 3D case or 2D case, how many components we have? We start to see already the complication. We see that we have 9 components or 6 independent components here and 3 components here. So which stress value should I compare it to compare it to the strength? Should I compare the normal stresses? Should I compare the shear stresses? And besides, we have another question. What if I rotate the cube in a different direction and I want to find what are the normal and shear stresses on this particular plane? Then what happens? So which one to compare? Even in 1D, we can ask the same question. Should I compare my stress in a particular angle or should I find the principal stress direction? But since it is a 1D problem, we cannot go to any other direction. But still, even in 1D case, we have seen when I rotate the plane on which I calculate the stress, there is a direction in which the normal stress is maximum. There is another direction in which the shear stress is maximum. So which one to compare? So we need a good failure theory. Okay, and this is not a straightforward question. When you do the experiments, you will later realize that we actually require efficient failure theory to represent ductile materials and brittle materials. Okay, so this is the need for failure theory, static failure theory. So what do these failure theories do? Failure theories propose appropriate means for comparing multi-axial stress states, especially to the strength. How do we compare? In what way do we compare the multi-axial stress states to the strength values we obtain from uniaxial tests? Okay, so it is usually based upon some hypothesis. A theory will have an hypothesis and then we will try to experimentally also determine whether the hypothesis is right or wrong. Some failure theories, they will be suitable for a particular type of materials and some other different types of failure theory. Okay, so let's go and see some of the failure theories, especially for ductile materials. Okay, so whenever we talk about yield phenomena, yielding, it immediately tells you that this is for a ductile material and not for a brittle material. Okay, yielding does not take place in a brittle material, only in a ductile material. So first we go through what is called as the maximum principal stress theory or the maximum normal stress theory. According to this theory, what it says, when the maximum principal stress does not exceed the yield strength of the material, then the failure doesn't happen in the case of ductile materials. We can find these principal stresses if it is a complete 3D problem. We have to solve a cubic equation using MATLAB and obtain the principal stresses. If it is a 2D problem, we can use Morse circle method to obtain the principal stresses, or we can use the formula directly. Then once we have the principal stresses, we arrange these principal stresses in a particular order. Sigma 3, and then taking the maximum principal stress value, we can maximum or minimum, because the minimum value can be negative and can be a very high value. We can compare it with the yield strength in tension or compression and then come to a conclusion whether failure will happen or not. But is this theory good? We will see that for ductile materials, this theory doesn't work well, and we will see the experimental results as well. So for the maximum principal stress theory in the 2D case, let's just assume it is a 2D case, and in which case you are going to have sigma 1, the principal stress value in the direction of the principal stress plotted on the x-axis, sigma 2 on the y-axis. We are going to normalize these stresses with respect to the yield strength, sigma 1 over Sy and sigma 2 over Sy. Let's suppose we do some experiments. Okay, we apply tensile loads, and based upon the tensile loads, remember this, in reality we are dealing with 3D specimens. Although we apply tensile loads in one direction, in a particular direction maybe we have failure here in one direction. If we apply only a tensile load as a 1D problem, we are going to get sigma 1 value here, somewhere near this guy, an experimental data. But let's suppose that you take a bar of the material, you apply load in different directions, tensile loads in different directions, then you will get some other failure points. So for example, here, etc. Depending upon the direction in which you apply the load and the magnitude of the load in particular direction and the magnitudes, you will have different failure points. So these are the different failure points when your principal stresses are all positive and they are not negative. Now let's suppose one of the principal stresses is positive, the other guy is negative. How does it behave? Then we get these data points. But according to the maximum principal stress theory, the failure envelope of the maximum principal stress theory is given by this dotted line here. If each of the principal stress values are less than the yield strength value, less than 1 value, if this ratio is less than 1, then no failure takes place. But we see in this fourth quadrant, experimentally, that is not the case. What we see here is, even when both the values are lesser, failure takes place in certain directions. When we apply stresses in certain directions such that one of the principal stresses is positive, the other principal stress is negative, then failure occurs within the failure envelope. So the maximum principal stress theory does not work for ductile materials in particular. Why do we have this discrepancy? So let's go to the next theory that will clarify it. We go to the maximum shear stress theory. According to this theory, the failure or yielding of the ductile materials begins when the maximum shear stress in the material exceeds the yield strength value. So exceeds the shear yield strength value. So in other words, we find tau max, and tau max value will be usually when you arrange in 3D in the form sigma 1 equal to greater than or equal to sigma 2, then 3, the highest values. Tau max we will calculate as sigma 1 minus 3 over 2. And if this value is less than or equal to the shear yield strength, then no failure. So this is the no failure. Otherwise, failure will take place. Usually the shear yield strength, SSY, is related to the yield strength in tension by this relationship, SY over 2. So that is what we have here. So let's apply this theory and get in 2D case, let's say in the 2D case, what is the failure envelope? If you look at the failure envelope, let's just go to the failure envelope first and then come back. If you look at the failure envelope, this is how it looks like. Very different from the failure envelope. What we have seen here is just looks like a square here for isotropic homogeneous material. In the case of MSS, we see maximum shear stress theory. We see the failure envelope is modified on the second and the fourth quadrant. So let's see the failure theory. What are the equations of the failure theory? So the tau max value sigma 1 minus 3 over 2 should be, if it is greater than or equal to Sy over 2, then failure takes place. Otherwise, we can rewrite this equation. This is the equation sigma 1 minus 3 greater than or equal to Sy. We can incorporate a factor of safety here if required, and then in that case we can divide by n here, factor of safety, to ensure that we have a failure doesn't take place and the stresses don't go near the limits. In other words, factor of safety n can be calculated as SSY in the numerator, which is equal to Sy over 2 over tau max. This is how you calculate the factor of safety according to the maximum shear stress theory. Now let's take the different cases where sigma 1, sigma 3 both are positive, one of them is positive, one of them is negative, different cases into account. So there are 3 cases we can come up here. Both sigma 1 and sigma 2 are positive. So we take the sigma 1 value as sigma A, sigma 3 value as sigma B, and then continue here. And we can see here both are positive or both are negative, or one of them is positive, the other is negative. So 3 different cases. So what are the formulas we should consider? So here, in case 1, when both are positive, what we need is just one value, sigma A value, and we can compare the sigma A value with the yield strength value. If it is lesser than the yield strength, then no failure. If it is greater, then failure has happened. So this is the condition for failure in case 1. Case 2, one of them is positive, the other guy is negative. In that case, we use this formula here, tau max greater than Sy over 2, or this quantity should be less than Sy in the case of no failure. Okay, so this is the equation here. What is the equation here for this slide? The first case, we have this case sigma A, exactly these 2 lines. And in the case 3, when both are negative, then we take the lowest value sigma B, and that value should be less than or equal to, if it is less than or equal to minus Sy, then failure. If it is greater, then no failure. Okay, so we are in this quadrant. Okay, so the less than or greater than or equal to symbols will reverse in the negative direction. So in short, we will not have any failure if we are within this failure envelope in the maximum shear stress theory. Let's compare the experimental values. You see the dotted line here that represents the failure envelope for maximum shear stress theory, and we can see all the failure points are outside. The experimental values are outside the failure envelope for maximum shear stress theory, And therefore, this is a very good theory for ductile materials. Now, why does this theory work so well? Simple. In a ductile material, all failure takes place to exceeding shear stresses. We have seen that in previous chapter, where the exceeding shear stresses lead to slip phenomena in the ductile materials. Due to the slip phenomena, we have plastic deformation. So it is shear stresses which are responsible for failure in the ductile materials, and therefore maximum shear stress theory works very well for our case. Okay. Next class, we will go through the distortion energy theory, and you will see that this theory accurately represents the failure envelope for the shear stress failure envelope, much more close to the failure envelope to the experimental values than the maximum shear stress theory. So you can see the maximum shear stress theory is much more conservative in that the failure envelope is well inside the actual points. But when we go to distortion energy theory, you will see an elliptical failure envelope. Let's see here. I don't have it here, unfortunately. So the failure envelope, if you see for the distortion energy theory, is going to be like a ellipse going around this point, approximately drawing the ellipse. And you will see this ellipse is very close to these failure points. Okay. Okay. So any doubt up till this point? If you don't have any doubt, please go online, inform. Okay, inform other classmates to go online on Teams and register their groups as soon as possible. You need to register your groups, start working on your project and assignments. The deadline for the assignments, I think it is next week. Please form the groups, inform your other classmates to do so. I will not extend the deadlines. So ask them to form the groups and submit the assignments. Okay. If you don't have any doubt, I'm going to stop right here and meet you again on Thursday. By the way, starting next week on Sunday, from Sunday onwards, we will have on-campus classes for those who have registered on campus. Besides that, I will also post a poll on your teams asking you whether you are interested to attend on-campus classes or online classes. Okay. The poll will not be, it won't be anonymous. It will be available for everybody to see. Whatever is your interest, you can post it, because I need to see who are interested to come to on-campus for teaching. I will not make it anonymous voting. Okay, so most probably tomorrow or day after tomorrow, I will make the voting on Teams available. Those who are interested to come to on campus, they can vote for that. Otherwise, you can vote for online classes. Okay, so see you guys, and I will meet you on Thursday again.
Okay, thank you, Doctor.
Doctor, for